F equals ma. Newton's second law states that if we have a mass and we apply a force to it, then that mass will accelerate. And remember that when we say acceleration, we don't necessarily mean this idea of here's a body and it's doing velocity of 0. It has a speed of 0. And then what we do is we apply a force to it, to this body, and then it accelerates. And the traditional way of thinking about that is you apply a force to somebody, some mass that's doing 0 speed, and it accelerates in a positive direction. But remember also, we can apply a force to something that's already in motion, that has some speed v. Okay, we'll say that's speed v. If I apply a force to it, and I'll make the force in this direction and constant, how might I do that? Well, it could be the situation where we're talking about a rocket ship, or the space shuttle. I use the space shuttle a lot because there's no friction involved, or very little friction involved, and we apply a force to it to the right in this direction, and that force is constant. It might be ejecting gas out of the side of the body. If it ejects gas, in which direction? In that direction, this F here. The force is in that direction. The gas will be ejected in the opposite direction to apply that force. And this is what we're getting to later. So there's gas here, applying this force in that direction. In which direction is the space shuttle going to accelerate? Everybody says, well, it's going to accelerate to the right in the direction of the force, isn't it? The acceleration will be in that direction as well. And we know from our uniform circular motion that if that force is constant, then the body will start moving in uniform circular motion. Okay? So an acceleration can be a change in velocity, which is just simply a change in direction, of course. There's also this situation where we have some body moving with some velocity, v, and we apply a force in the opposite direction to its velocity. What happens to it? It slows down, and we say it decelerates. That's the common thing to say. It's actually negative acceleration. In which direction is the acceleration? Same direction as the force, isn't it? Okay, so the acceleration is in that direction. Even though the body is still moving to the right with some speed, it's accelerating to the left. Okay, then they go on to say also we have these accelerations which we know under the influence of gravity, G is always down and towards the center of the Earth. Here's another type of acceleration. Oh, it's acceleration all the same, but this is the one that's responsible, that is caused by gravity, of course. That's governed by Newton's second law as well. Newton's second law is this. If we apply a force to some mass, then we have an acceleration in the same direction as the force. We also know that that acceleration is equal to the change in velocity over the change in time, average acceleration, okay, which of course is equal to v minus u over the change in time. An example. I'll just make this picture bigger for a second. It's a bit hard to see. they're calling this here VI or U. So they're giving it both its names there, and they're doing the same over here, VF or V. And the picture that's that's been drawn here is this ball is striking. This is a wall, striking this wall at 40 degrees to the wall, and bouncing off that wall at 40 degrees to it also. It's moving in this direction. Initial velocity, final velocity. Now they're saying that these are two vectors, so they should have arrows on them, and we'll redraw this diagram. Let me just make this a little bit smaller first. Move it across. I better make it smaller again. Okay. A ball of mass 0.4 kilograms and moving at 10 meters per second collides with the wall at an angle of 40 degrees. It rebounds off the wall with the same speed and the same angle with the surface. The duration of the impact is 0.2 seconds. Find the average acceleration of the ball during impact. Let's draw this diagram again. And I use Illustrator because I can draw straight lines with it. It's quite good, but I'm not used to it, so you have to bear with me. I'm not used to drawing straight lines. We'll make the wall. I made the wall orange in the last one. Make it a little bit more sizey. That's our wall, and this is the path of our. Oh, yeah. Better deselect it. Is it still selected? It is, isn't it? There we go. Here's our ball coming in. It's not really 40 degrees, is it? And bouncing off the wall. And we'll label these vectors. Make it a little bit fatter. U and V. If they are in fact vectors, then they need to have directional arrows on them. U is going in that direction, V is going in that direction. How would I draw minus U? It's in the opposite direction to U, isn't it? I'm going to add it to V though at the same time. Okay. And that's now minus U. And I've added it to V. Why have I done that? Well, yes, that's right. Yeah. It gives me this resultant, doesn't it? And what's the resultant? The name of the resultant? Delta V. Yeah, that's right. Exactly. Delta V. And why do I want that? Because I want the acceleration. We know that acceleration is equal to delta V over delta t. And we already showed before that delta v is equal to v plus vector addition minus u over delta t. I've got to now work out what that delta v is. We know that that's 50 degrees, don't we, in there? 50 degrees. Yeah, this one was 40, so that one's 50. If that one's perpendicular, or it's supposed to be. I know it's not quite perpendicular, but I can split those two in half. This is an isosceles triangle. Those two vectors are of equal magnitude and hence length. So it's isosceles. I can split it in half, draw a right angle, and then I know that this is delta v on 2, this line here, and this is delta v on 2, this line here. Okay, so we might say that. We might go delta v divided by 2 is equal to what? Well, let's go back to Sokotoa. Cos of 50 degrees is equal to adjacent over hypotenuse. I know what the hypotenuse is. I know the angle. I just need to know this side here. Okay? So I'll delete what we did here. Cos theta equals adjacent over hypotenuse. Cos of 50 degrees is equal to delta V divided by 2, put that in brackets, over, what was our V, was 10 meters per second. From that, we get delta V on 2 is equal to 10 cos 50. Can somebody calculate for me delta V? 15.32. Radians. We got a different number last time. Which one is correct? The wrong problem here. Hang on. Oh, here we go. 12.85. 12.85. Now that's a velocity, meters per second. We haven't found our acceleration yet, have we? Acceleration, I'll just move up here. A equals delta V delta T, which equals 12.85, 0.2 seconds for the time. 64. Yeah, that's okay. 64.3. Quiet, please. Meters per second squared, because we have an acceleration. There's something we're missing here. Direction. In which direction is the acceleration? Now we're looking at the acceleration of the ball at this moment here, aren't we? This moment when it strikes the wall. Yeah. I'll say perpendicular to the wall. And to the left. And out from it. And that gives our direction. That's our acceleration. Question 2 asks, the force that the wall exerts on the ball. This follows on from our last question, force equals mass times acceleration. What was the mass of the ball? 0.4 times by our 64.3. 25.72. What? 25.72 watts. Newtons, isn't it, is a force. And there's something else that I need to add. Direction. Which direction is the force? Same direction as the acceleration. Perpendicular to the wall. And out, away from it. Okay. That's not so hard. 3. Whoops. Yeah, I think it won't change back for some reason. I don't know why it does that. Yeah. The next question says, we'll stick with this. That's okay. This is almost the end of the page. It says, what is the? So that was the force on the ball due to the wall. What's the force on the wall due to the ball? Yes, that's right. By Newton's third law. Action-reaction. We can say that it's 25.72 newtons. And into it, and to the right. Oh, what did I just do? Yeah, okay. I've got a question for you guys to do. Hey, how much time have we got? 5 minutes? Maybe 4? 4 minutes is enough for this question? Here's a similar question. I'll get you a picture as well. Ball of mass, 200 grams, please. Ball of mass, 200 grams. Be careful your SI units there. Moving at 2 meters per second. Rebounds at right angles off the side of the billiard table. With a velocity of 1.6 meters per second as shown in the diagram below. If the duration of the impact is 0.2 seconds, calculate the average acceleration of the ball during the impact. Now, notice that they've got, this is a one-dimensional problem, and they've set their final velocity as minus 1.6, so they've given it some direction in that way. See if you can have a go at this, please.